That's the signal and mass transport. As you know, we have this global warming these years actually, and ice ice are melting, and water enters the ocean and sea level, and the sea level rise. That's a big risk for the big risk for floods and many other issues related to human life. Therefore, we need to monitor how the water move in land and how the water move in over ocean. Here we are, when we talk about hydrological signal, we mean that we monitor the water in land. So we need to see how the gravity field and its temporal changes, I mean the changes in time, can be related to these hydrological effects, hydrological or water variation. So let me start with again with the well-known Newton integral, and consider that if we have the change in the potential of this, I will write surface mass. If we have mass, this is like a layer at the surface of the earth, and at the position or the top and lambda. In Newton integral, as usual, we have a surface integral and we have a radial integral, r from r plus delta h. Delta h is a very thin layer at the surface of the earth. And I have the density change. This density change is, of course, I will write it here in three-dimensional form, but later we will see that for the thin surface, we only consider its lateral variation. So again, as you have already seen, this L, what exactly I would say L, or 1 over L, can be expanded into the Legend series. So I will write simply delta V Sm in surface mass. I do not write this one, it's long. I will write G over is the integral surface, and instead for this L, I will write the Legend expansion. So R integral R plus delta H, again delta rho R prime delta prime dr prime Pn x bar is the cosine of psi. Psi is the geocentric angle between the computation and integration point. Yes. One point that should be discussed here is about surface mass. What can we do with the surface mass? So let me write this R prime. Oh, I have missed this R prime. Let me write this R prime over R n square. I missed this R prime over R n plus 2 here. Let me write it in that form. R plus the thickness of a very thin shell, and I can approximately write that it is R over R will be 1 plus delta H over R over R. But I have is 1 plus 2. It is approximately 1 because delta R is considerably smaller than R. This is approximately 0. Then I can ignore this term, or I can put 1 instead. So in that case, I can write the whole equation like this. So I will write surface I define surface density, which is actually integral R plus delta H delta rho R prime delta prime and delta R prime. So I change this to the surface density. Here we have a three-dimensional density changing with the distance from the center, colatitude, and longitude. And when I take this integral, it means that I'm somehow averaging it along this thickness. Since it is so small, it is a very thin layer actually at the surface of the earth, which has the density delta rho. And this density changes by the latitude and longitude, not with the radius anymore. Then this is called surface density. So if I use this surface density to this the surface mass at the surface of the earth, I come to this equation. And again, I will have this double integral, and I have delta rho and surface, which is theta prime and lambda prime this time, P and x bar. Okay. So we could get rid of R, the radial one integration parameter, and now we have to transfer this to spherical harmonics directly. And if you remember the addition theorem, Pn x cap x bar tilde is 1 over 2m plus 1 summation m minus n till m y and m theta and lambda integration point, computation point, and integration point. If I insert this back inside this formula, I will get that the potential change due to changes in the density or surface density can be written in this spherical harmonic form: 4 pi summation from 0 up to infinity 1 over 2 plus 1 summation minus 1 delta rho and m surface density, spherical harmonics of the surface density, theta and lambda. So this is the potential that we can get from the surface density, or the potential change due to density change. And this density change, as you know, as you remember, is nothing else than rho and m. You have seen this many times, spherical harmonic analysis. So if I have the surface density, theta prime lambda prime, and we have spherical harmonics. That's it. So if you have a surface density change at the surface of the earth, it could be water, it could be whatever, this would atmosphere, then you can compute the spherical harmonics of the density changes. When you insert these density changes inside this spherical harmonic, you get the potential change. So we could see that these density changes at the surface can be connected to simply to the potential changes. But it's not all, because we need it in the term of the potential, gravitational potential. Let us write the changes in the gravitational potential, the spherical harmonic change, which is actually the changes due to the surface and changes in the solid Earth. So it's not only the potential, the changes in the gravitational potential. It's not only the surface. Even inside the Earth, something will change, and then we can see this change in the spherical harmonic coefficients. This term has been written that it is Kn times of the surface density. Kn is log number. It's log number. So if I consider this Kn, which is actually the ratio, it's almost 0.31, and it means that the changes inside the Earth is 30% of the surface changes. So if I insert this back inside this spherical, this formula, then I can say that the total changes in the gravity or harmonics of the gravity will be 1 over Kn surface changes. This is the principle that John Ward has derived. So if now I insert this, I use this principle, and I have also already have the surface mass changes. Surface mass changes was actually, if you remember, surface mass changes was already 4 pi gr, if you remember, was summation, and it was 1 over 2n plus 1 summation m minus n, and then we had delta rho and my and m. Then it was for the surface density. So it gives you the, if we consider that this term was surface density, then this relation is also valid for delta rho. Therefore, I can write 1 plus K1 changes of the surface density. So in that case, this can go directly here, 1 plus Kn. So in this case, I can say that the surface mass, the potential of the Earth, is this, the surface due to this term. So therefore, we could find this effect, or the changes of the, due to the gravitational, the relation between the surface changes in the surface density and the changes in the gravitational potential. So then we will come to hydrological effect. So delta rho, I will write total water storage, is the density, surface density, is total SM. SM stands for soil moisture. It's the soil moisture plus delta rho, SWV, is snow water equivalent. This density changes due to the snow melting, and delta rho can stands for canopy of trees from trees plus delta rho GWS, which is ground water storage. So the total water storage, I write it, total water storage is a summation of different density changes due to total water is from the soil moisture, snow water equivalent, canopy, and groundwater. So if we have these densities or their harmonics, like let me write it Mn in front of them, and insert them back into this equation for the potential, then simply we can derive the gravitational effect of them. So if you remember, then the changes of gravity was 4 pi g or summation n0 up to infinity. And here we have 1 plus kn 2n plus 1 and summation minus n. And here I will write delta rho soil moisture and m, snow water equivalent and m, and canopy plus and m of course, and m, and groundwater storage y and m. So if I write this delta v in the spherical harmonics form, spherical harmonic coefficients, then it will be 4 pi g r 1 plus k 1 plus kn over 2n plus 1, and these densities nm soil moisture plus rho and m SWE plus rho and m canopy plus delta rho and m ground water storage. So this is the total potential, or total potential due to the mass transfer or changes of the mass inside the one. So if you have these changes, then you can determine this total mass change. Or if you have the total mass change, you can determine potential. So what we get actually from grace or grace 4, grace long, is changes of this spherical harmonic. Of course, not the changes you will measure. They will determine from the measurement the monthly data or time variable gravity fields. Then when you subtract them from each other, you can get the variation from month to month. So from these variations actually represents this mass transport. And the formula that I have shown to you, if I want to solve it for delta v, if we consider this as noun, therefore this density of soil moisture, you see harmonics of soil moisture harmonic of snow water equivalent plus harmonics of the canopy plus harmonics of the groundwater storage will be, so if you remember 2m plus 1, then I have to solve this equation in that way, and 1 over 4 pi gr changes of VNM. So this means that if I compute the variation of the gravitational potential, I can come to density. But this is the total density. And now imagine that I have a hydrological model which gives me this tree normally. Soil moisture from hydrological model. Logical model. Snow water also from hydrological model, canopy. And if I consider that they are known, I can determine the groundwater storage. Simply. Therefore, the groundwater, the surface or the density, surface density of the groundwater storage or the fresh water will be 2m plus 1 over k1 plus kn one over 4 pi gr changes of from grace, for example, I would write grace minus rho m soil moisture, snow water equivalent, and from canopy. Then we have the surface density. So, and if you want to see, you want to get the height, actually, height of that. So these are this. You can simply write all of these terms in terms of the potential instead. For example, if you want to have it in terms of the potential, you can write V and M. Then you should multiply all of these terms to get the potential in terms of these things. In terms of potential, it will be the potential of groundwater storage will be, then I multiply 1 plus kn over 2m plus 1, they multiply by these densities. So in this case, this term will be of the potential, and this one is from the base. Then if you subtract them from this one, then you get the potential. I have forgotten 1 over 4 pi gr as well here. So if you have the potential of this delta, and if you divide it by gamma, based on the Brunn's formula, you can find the height of the groundwater. So therefore, it will be simple to compute based on this principle the total water grounded. But in hydrological models, they will compare this they will compare the densities with density of water. So if you see density of water here in somewhere here, don't be surprised because they are they are in the based on hydrology. So therefore, the groundwater storage, or the height of the groundwater storage, let me write the groundwater storage, will be simply rho W, density of water, 4 pgr gamma, and summation over nm, and it will be 2m plus 1 plus km, and delta Vnm of grace minus the potential. So that's the whole story for monitoring the water changes the surface of the earth by gravimetric. We can also monitor earthquakes by from the changes of gravity field. The principle is that, for example, the GRACE mission measure provides or give the monthly gravity models. So we need some models before earthquake and some after earthquake. So here is the earthquake. Of course, the size of the magnitude of the earthquake is also important. When it is large, it's easier to detect it by satellite or GRACE data or GRACE 4 data. But the smaller earthquake is a little bit harder, so of course, because of the distance and sensitivity. So one important issue for monitoring the earthquake is that the effect of hydrological signals should be computed and removed from the gravity changes or gravity mass. So it means that if I want to see changes of the gravity, I write in spherical harmonic, for example, then this spherical harmonics of, for example, from GRACE should be corrected by the spherical harmonic from hydrological signals. So we have discussed this before, how to model this from the surface density of this. So these informations are available in hydrological model. For example, GLDAS is one of these models, which is has a good agreement with GRACE models. So you should consider the changes of the gravitational changes of this hydrological effect on the gravity, changes that they create and they make in the gravity, and you remove them from the GRACE gravity changes to come to the earthquake signals. So it is very important that, of course, the quality of the hydrological model that you use is important when you want to. So that's important. You can, from this spherical harmonic expansion, you can generate delta G or first or second order derivatives of the gravity, or tensor of gravitation for monitoring the earthquakes. So it doesn't matter which one, but when you take derivative, you will amplify the signal. It means that if the earthquake is near surface, then it should be easier to detect it by the derivative or the gravity anomalies than if they are deep inside. So another issue that I should need to